Good trick. Good trick.
I think we are good to go. So, okay, so today we're happy to have our own Dror Varolin to talk about Hilbert spaces of sphere integrable holomorphic functions. Let's welcome.
Thank you. And I will start with applause. Okay, so actually, surprisingly, it's the 100th anniversary of the introduction by Bergman of the Bergman kernel. So exactly 100 years ago, a paper appeared that introduced this idea. It's an important thing, but nobody loved it more than Bergman, I think. So, he was famous kind of for cornering people and talking to them about the Bergman kernel. In fact, once he tried to convince 60 Minutes to do a 1-hour episode on the Bergman kernel. So it never happened. But. Okay, so, well, there's something that people call the Bergman space. That wasn't me, right? Okay. So, I'll write it in generality. Omega will be some open subset of Cn, and then I'll use a H for holomorphic or Hilbert space of omega to be the set of all holomorphic functions whose integral with respect to Lebesgue measure is finite. So Bergman's sort of crucial observation is something called Bergman's inequality. So for all f holomorphic in omega, and for all compact subsets of omega, there exists a constant which depends on this compact set. So such that for every point P in K, the absolute value squared of P is less than or equal to this constant times the square of the L2 norm. Actually, it's over K, I guess. So this is called Bergman's inequality. And it tells you in particular that... Sorry?
Does it work with Ks measure 0?
Yeah.
Wait.
Oh, sorry.
Omega, maybe.
No, it should be omega. Sorry. Yeah. Right. Yeah. So the point here is that if you have a sequence that converges in the L2 space, then it gives you a bounded sequence in the L infinity norm, at least locally on a compact set. And then Montel's theorem tells you that that converges, a subsequence will converge to a holomorphic thing. So that tells you that this space is closed inside the L2 space. So if you forget about holomorphic, so this is a closed. So in fact, the inclusion is compact, but I won't use that particularly.
Why is it true?
Why is this true? That's basically the Cauchy formula. If you integrate it correctly, there's a bunch of different ways equivalent to that to prove it. Yeah. Right. So, and once you have a closed subspace, that's the same as having an orthogonal projection. So it's just an orthogonal projection. And because you're in an L2 space, it has some kind of Schwartz kernel, but this is a kind of a Euclidean picture, so it's very easy to write down the Schwartz kernel. And so this Pf of z will be the integral over omega of k of z w, f of w, dv of w. And then this k of z and w will just be the sum. Well, let me just write over j. This could, in this picture, you'll have infinitely many, but later we won't. the kernel will have this form where this Fj is an orthonormal basis for the subspace. Right? So that's, okay. And this object, P is called the Bergman projection, and K is called the Bergman kernel. And it contains a huge amount of information about the domain in good situations. It depends a little bit on the domain, and I'll come back to that in a little bit. But maybe one way to see, one kind of approach to studying domains up to complex structure is to say, well, okay, they're determined by their ring of holomorphic functions, but that's just entirely too large. If you take an L2 subspace, that could shrink it significantly, even though it's still a large space. And then up to unitary transformations, that's all contained inside this Bergman kernel. So that's kind of where the information is packed in. And I'll state a couple of results about what kind of information you can extract from this. Maybe just one thing to note is that it's extremely difficult to get any explicit formulas for K.
Uses the play volume.
Yeah, so I'll come back to that too. Okay, if you want, I can just say something quickly about that because it's going to come up again. So that's true. So this thing is not just about the complex structure if you read it in this way. But in fact, since this is a domain in Cn, in the canonical bundle of this thing, so the thing whose sections are forms of top degree of type 1, 0 top degree, that's going to be trivial. So it'll be n0. That's why I said 1, 0 of top degree. I guess, yeah, I said n there, so I should just say n0. Right, so instead of doing this, you could take things of the form f dz1 up to dZn. These will be holomorphic forms of top degree, and if you wedge them with a complex conjugate and multiply by an appropriate multiple of plus or minus 1, yeah, that will give you a natural invariant of just the space. But we'll soon be interested in more than just the space. Okay. Sure.
If you do it that way, then you can set it up so that...
I will be using this for something. Yeah. So this eliminates the measure. But there are other things that can come in that are important.
But if you have a domain that has a lot of automorphisms, you want to say this is an invariant under it, right?
Right, so that's right. So that will follow. Well, you have to be a little bit careful because that can modify this thing. So it really depends what the Jacobian of the automorphism looks like with respect to the L2 structure. So you should be more careful than that. Okay. Right. So as I was starting to say, it's extremely difficult and to get explicit formulas, and sometimes even if you can, they're not particularly useful. But there is one simple case which is actually very useful, and that's the unit ball. Unit ball, so I'll call it B. That's the set of all Z with modulus less than 1. Then you can write down the Bergman kernel exactly. So the point here is that in that situation, the monomials are pairwise orthogonal, and you just have to compute their norms. And when you do that, it gives you a summable formula. And the outcome is that this K of Z and W will be n factorial over pi to the n, 1 over 1 minus Z dot W bar to the n plus 1. So, okay, now there's another thing to observe about this thing. It's a holomorphic function of Z, but it's also a holomorphic function of W bar. So, in fact, it's a holomorphic function on the space omega cross omega bar, where you give it the complex conjugate structure. And inside here, you have something which is kind of like the diagonal. So it's the set of all Z and Z bar. And this is This is a totally real subspace with respect to this complex structure. And so if you know the Bergman kernel on this diagonal, then you know it everywhere. It's just like knowing a holomorphic function in the domain on the real line. Okay, so let's say if we write k of zz, that's n factorial over pi to the n, 1 minus mod z squared to the n plus 1. And if you, for example, take the function rho of z is, so mod z squared minus 1, then it's negative exactly in the unit ball. And functions that are negative on a domain, and if the domain is smooth, the differential shouldn't vanish on the domain, are called defining functions. We will use those in a little bit. But one other observation about this thing, if you take the logarithm of k of z, and then you take the square root of minus 1 dd bar of that, then that will be, well, this will be, it's a Kähler form. So it's actually a positive 1-1 form. So from it you can make a Kähler metric. Maybe in the case n equals 1, it's worth writing down exactly what it is. So in this case, it's very easy to calculate. So this will be 2 square root of minus 1 dz wedge dz bar over 1 minus mod z squared. So that's a Poincaré metric for the unit disk. And this one normalized, I think, to have curvature minus 1. But you can take other normalizations. Okay.
Analogously, is it Poincaré metric and higher disk?
Well, I don't know what that is,
It's complex hyperbolic space in dimension n. So it's a Riemannian symmetric space. Is also Kähler. That's constant.
Yes, it's still and it's also still a Kähler-Einstein metric. Okay. Right, but anyway, I don't want to get bogged down since I have a lot to say.
KZW?
Yes.
Why?
Because, as I said, the diagonal is a totally real subspace of x cross x bar. So this is the version of polarization that doesn't work with just polynomials. It's the analytic version of polarization. Okay. So because of this fact here, that it's extremely difficult to get any kind of explicit formula for this thing, people wanted to try to get asymptotic information. One of those, the first person to do something serious was Hermander. Who did this while he was visiting Stanford, and he tried to tell Bergman about it and then regretted it because he got cornered. But anyway, so Hermander proved the following. Well, yeah, okay. I'd like to state this. At some point I'm going to have to cut something. So you have a domain omega, which is defined by a function rho less than 0. Let's say this rho is a C2 smooth function. And then I can rescale the function so that the differential is 1, so at every point of the boundary. So you can think of rho as maybe the negative distance to the boundary, at least near the boundary, and then what it does inside doesn't matter so much. And then now you have to assume something about the domain. So assume that, well, yeah, okay. So assume that this d bar operator, so from L2 of omega to 0, 1 forms with L2 has closed range. And now you let Z0 be a point on the boundary such that the boundary is so strictly pseudo-convex near this point. I'll say what that means. But I'm not, I don't know if it'll really help, but so
For example, right? So maybe
yeah, that would be, yeah,
that would be more than you need.
strictly convex, yes. Okay, so maybe I'll you take Claude's advice and say, e.g., strictly convex. So, but I'm just asking for this. In fact, strictly pseudo-convex turns out to be equivalent to strictly convex near the point. But after a turn, yeah, near the point. But anyway, so oh, maybe I still want to say this. Okay. Well, okay. I don't want to get too bogged down in this, so I'll say something like this. So then the limit as z goes to z0, but inside omega so you take this defining function, so negative, take its negative to make it positive inside the domain, divide it by the n plus first power, multiply by k of z, and take the limit as z goes to z0, and that's equal to so some constant times, well, I'll call it L of z naught. So this is a number that measures the curvature of the boundary of the domain along the tangent spaces in the boundary that are invariant under multiplication by the square root of -1. So it's called the Levy form, and this quantity is the determinant of the Levy form. So it doesn't matter too much. The point is that this Bergman kernel near the boundary behaves a lot like the Bergman kernel for the ball. It looks like 1 over the negative defining function to the power n plus 1.
How can you not like this?
It's a great theorem. No, I mean, Bergman loved it because it was, he loved it because it was about his kernel. But then,
That's what you call right telling, right?
no, you tried telling him and then he regretted it.
Oh.
That's all.
Oh,
No, Bergman was ecstatic.
Oh, okay.
Okay, so then, all right, so that's a very nice result, but it's kind of hard to do a lot with it because it's just an asymptotic limit. For example, if you try to differentiate this, you run into serious trouble. So about a decade later, Charlie Pfefferman considered that situation, and he proved the following theorem. So this thing was in Hormander's famous ACTA paper in 65. This is done in 74 by Pfefferman. So he proved that, I'll just write it quickly. So k of z is equal to, so f of z over negative rho of z to the n plus 1 plus g of z, a log of negative rho of z. And here, these f and g are smooth functions. Oh, and here you need the boundary of omega to be C infinity smooth, not just C2. These guys would be smooth functions on some neighborhood of omega. So why did Pfefferman do this? Well, I won't write it down, but I'll sort of explain what his goal was. So at around 20 years before that, there were these things called the Chern-Moser invariants. They're boundary invariants of the boundary of a domain. And there was a desire to know that those invariants characterize the complex structure of the domain itself. So one way to do that is to prove that if you have a biholomorphic map between two domains, then it could extend to the boundary and give you a diffeomorphism of the boundary. Then you would
The smooth
have
extension.
exactly. And so Narasimhan had this idea that, you know, if you look at the Poincaré metric, then the geodesics intersect the boundary perpendicularly. So you could try to push diffeomorphisms along the geodesics to get a smooth, biholomorphisms to get a smooth diffeomorphism on the boundary. And Narasimhan suspected that maybe you could do the same thing for the Bergman metric, which is this quantity here. And in order to do that, you need to know how it behaves asymptotically near the boundary. And Pfefferman, the first theorem in this Invenciones paper is this, and the second theorem is the theorem that proves that the geodesics are sort of transverse enough that you can do this. And I think nobody understood either proof. And so shortly afterwards, Boutet de Monvel and Sjostrand sort of simplified Pfefferman's approach by introducing some microlocal analytic techniques, a little bit more symplectic, a little bit less relying on something called the D-bar-Neumann problem. And it became easier to handle. And then the boundary extension thing turned out to be not so reliant on the Bergman kernel. You could do this in a kind of softer way using some functional analysis, and that was done by a different group of people. But in any case, the kernel was an important actor in the beginning.
All of these Moser invariants computed on the boundary are actually holomorphic invariants on the interior.
Yes, that's right. If you have a smooth boundary, and then people could reduce that regularity to some extent. Okay, right. So now I want to.
You should emphasize that your n is bigger than 1, right? So you don't want to. I mean, there's several complex variables are really different from one complex variable in this respect. You don't have these CR invariants.
No, you don't have the CR invariance, but you definitely have the biholomorphic extension to the boundary. Right, there's a Riemann mapping theorem, so there's really no... I mean, in some sense, this was all guided by the failure of the Riemann mapping theorem in several variables. Okay. These are very old stories, and I want to get to more new stories, but they're so fun to talk about. I'm going too slowly. Okay. So now, this theory works really well if your L2 space has a lot of holomorphic functions. But there are some L2 spaces that don't have a lot of holomorphic functions. For example, if you take omega equal to Cn. Okay. Then, of course, the Bergman inequality still holds for, say, any ball. But then you get that you have a bounded, if anything that's in L2 of Cn is actually bounded and therefore must be constant, but if it's in L2 it must be 0. But that's not a very rich space. It's not going to tell you a lot about the geometry. So instead you modify it and you weight the Bergman space. So you define a space like Cn e to the minus mod z squared. So you can imagine what this is. These are entire holomorphic functions whose Gaussian measure, well, with respect to the Gaussian measure, they're in L2. And so this is still a nice space, and you can compute the Bergman kernel for it and everything. But of course, it relies on choosing some additional information. But that turns out to be a good thing. So, but it's discovered a little bit later, and I don't know the whole history of that. But so more generally, you can define these spaces. Okay, let me start with this. So you have X is a complex manifold. And then you have a holomorphic. I'll do it for a line bundle, but you could do this for vector bundles. So this is a holomorphic line bundle. Maybe H is a Hermitian metric. It just means an absolute value on every one of the lines that's varying in a nice way. And then you also pick a measure, mu, say a smooth measure, on X. And then you can define H of, so let's see, d mu H. So this will be the set of all sections such that the integral, so you can make an L2 norm with a metric and a measure on your space. So this should be finite. So this gives you an analog of the Bergman space, but now it's a...
Symbol inside the
that's an H. It's a Gothic H. I like to save the regular H's for functions.
H is
The metric.
Hermitian metric.
Yes. Yeah. Right. And if you have a smooth measure, this even works well if for metrics that are not exactly smooth and measures that are not exactly smooth, but it doesn't matter for us today. There's still a version of Bergman's inequality here that you do locally. And so that will still give you this compactness property for the inclusion into the corresponding L2 space, meaning you don't look at holomorphic sections. So that theory can extend everything that we've said into this more geometric setting, but now, as Dennis said before, it's going to depend not just on the complex structure of X, but also on the complex structure of the line bundle and the choice of the weight or Hermitian metric and the measure that you use. You can eliminate the measure again by, instead of looking at sections of L, you look at sections of L, so maybe the canonical bundle of X tensored with L, and then you can take an analogous squared norm. Okay. Bergman kernel, if you follow that whole theory again, it just becomes, so K of ZW has exactly the same formula, except maybe I'll write S. Where these Sj are now an orthonormal basis for that space. Right. And again, you can look on the diagonal. Well, okay, maybe you should say this is now no longer a function. It's actually a section of a certain line bundle. So, and then when you restrict it to the diagonal, it gives you a metric for the dual line bundle. So these things are all analogous to real valued functions. We don't have to know exactly what they are. So let me save time by not saying that. So what are the analogs of Hormander's theorem and Pfefferman's theorem? Oh, so now there are analogs, but they're not as exciting unless you impose something more on the manifold. So I'm going to also assume that X is now a compact Kähler manifold. I won't explain why it needs to be Kähler, but for some of these theorems it needs to be Kähler. But the compactness means now, well, there's a Hodge theorem that tells you that this space will be then finite dimensional. If you don't need something as strong as the Hodge theorem, it's the maximum principle really that tells you this finiteness. So it's that part of the ellipticity that tells you the finite dimensionality. So actually this thing just becomes a finite sum. Okay, so so here's the Hormander theorem for this situation. So here I just remind you that X is compact and Kähler and so on. So let's fix so H to X and then a metric H such that the curvature of this metric is strictly positive. And now let's take the line bundle L to be the mth tensor power of H, and the metric that we actually want there will be the corresponding mth tensor power of this H. And then we have the Bergman kernel that I'll index by this m. And I want to let m go to infinity. And that's how I'm going to get the analog of this statement. So Hormander's theorem turns into this. Limit as m goes to infinity of m to the minus n k of zz. So remember, this kind of a sum of squares of sections. I can take their norm with respect, their pointwise norm with respect. So m is some integer. N is the dimension of x. That's fair, I didn't say that. M I'm going to let go to infinity is a kind of semi-classical limit. So this thing will converge to 1 for some good choice of measure. So the measure I'm going to take is the volume form associated to the Kähler form here, divided by 2 pi.
Your Kähler form was already snuck in as the curvature of the long bundle.
Well, the Chern representative, yes. Right. And so, in fact, this implies that, so m to the minus n times the dimension of h0 of x O of L to the tensor m is equal to the integral over x of, so this is the volume form I was talking about, theta of h to the n over n factorial. So this is something called the asymptotic Riemann-Roch theorem. It computes, the Bergman kernel will compute the dimension of this space when the dimension's finite, because you're integrating a sum of pairwise orthonormal unit vectors. So you get 1 for each dimension. Okay.
Theta is some invariant.
No, theta is the curvature of the metric.
But you can think of it as just you're taking the nth cut power of the first Chern class of the long bundle. So is that
Yes, that's right. So here, this is a cohomological quantity, so it's just the Chern class. But sorry?
Like Gauss.
Yeah, that's right. It's exactly that. Yeah, a case of it, I guess. But right, and then. I won't write the Pfefferman version, but it's something called the Tian-Catlin-Zeldich asymptotic expansion. So there are people in this department, maybe even in this audience, that know more about this than I do. So I don't want to talk too much about this, but it plays a major role in the study of Kähler metrics on a given complex manifolds. It's a kind of quantization result. So the one last thing I'll say about this is that in some sense these two theorems are like the Fourier coefficients of these theorems. So if you think of something like the unit ball, it's sort of foliated by these lines and there's an S1 action. And if you, under that S1 action, you look at the Fourier coefficients of these functions, you'll get these theorems. It's vaguely speaking. So you can actually make this quite rigorous. But okay.
That would be for what, projected space or?
Actually, it'd be just for any kind of disk bundle. The total space of the dual of L is where it would work, for instance. So, but it's just to throw some words out there to make people vaguely interested so they could read more later. I don't claim to have said anything. So. Okay, so this is kind of the story, up to maybe the end of the millennium. So Steve Zeldich and Dave Catlin published that theorem simultaneously and independently around 98. Okay, so about 15 years ago, people started to wonder about what happens if you want to look at families of these Bergman spaces. You want to try to deform these Bergman spaces in some way. And you would like to be able to say something about the kind of information you get out of such deformation. So if anyone has looked at the theory of deformations of complex manifolds, for instance, it comes in many, many flavors, but it's always quite hard to understand. And it's really hard to say exactly what it does very easily. You have to introduce a lot of ideas. So there's going to be a little bit of that here, but hopefully I can tell you some things that you can extract from this deformation theory that are not abstract deformation theoretic. Okay. Okay, so a phrase like that could mean a million things, but I'm going to have it mean something quite specific. So I'm going to start with a map pi from a complex manifold X to a complex manifold B. X is the base, or B is the base. And I want this to be a holomorphic submersion. And so I'm going to state things very generally in which nothing interesting will be true. So,
Always proper?
no, not yet. Okay. So, and then you can define these Bergman spaces. So for each, yeah.
Implication, is there a limit also?
In which one? Sorry.
This implication, yes. Is there
Oh yeah, sorry. Yes, limit. Absolutely, yeah. Okay, right. So this is what you might think, but now I'm going to introduce the thing that Dennis suggested earlier. So I'm going to take alpha holomorphic sections of, so XB is going to be the fiber over B, which is a complex manifold. And so I can look at holomorphic sections of the canonical bundle of XB tensor with the line bundle. LB just means L restricted to XB. So I look at such things and I ask for them to have a finite integral.
So you also have a line bundle over X.
Did I not mention that? I'm sorry. Yeah, thank you. Yes. Trying to squeeze in a lot of stuff. There's also a holomorphic line bundle, and not only that, it's also equipped with a Hermitian metric. And now I can sort of pair these holomorphic top forms with values in L. I can take their norm, the norm of the L part with respect to the metric, and wedge the forms together, and then I get a comp. Well, this is a non-negative measure in this case. If I have alpha and beta here, it'll just be some complex measure, but it's a nice smooth measure. Okay. And I just ask for this to be finite. So this is a way, I want to eliminate choice of a measure because the kinds of theorems I want to state, I want them only to involve the curvature of H. Okay. So I remove that other. I mean, you could do the other thing, it just gives you messier statements. Okay, so then now you've got, for each point of B, you've got a Hilbert space of holomorphic sections, and you want to say that this varies in some nice way. So the first thing you do is you take sort of disjoint union of all of these things, and you call this, so H of H sub B. Okay. And then you have an obvious projection map. But right now, this is just a set. And I want to say that it'll have some kind of structure. So the way I'm going to give it structure is I'm going to tell you what the smooth sections are. Okay?
Probably don't want to subscript B.
Oh, no subscript here. Sorry, yes. I want to tell you what the smooth sections are. And maybe what so smooth sections will give it a smooth structure, holomorphic sections would give it a holomorphic structure. Another thing that could give it a holomorphic structure is that I tell you how to take the D bar of a smooth section. Okay, so, at this level of generality, it's not, so okay, the goal would be that this would be a vector bundle. If this were a vector bundle, then we could ask, it already comes equipped with a metric because the L2 norm, the square of the L2 norm, gives you a Hermitian metric on the fibers. And so you could ask what the curvature of this thing is, and then you can ask why you want to do that, and I'll try to say something about both cases. But unfortunately, at this level of generality, this cannot be expected to be a vector bundle. Okay. So I want to talk about two special cases.
Finite dimensional, they might not all be the same dimension.
That's one thing that can happen. But even if the fibers are infinite dimensional, And even if the thing looks like it should be a vector bundle, it might still not be a vector bundle. So the local triviality becomes a huge mess when you have infinite dimensional fibers, and it seems to involve some kind of real analyticity property, although that's a mystery. In finite dimensionality, as soon as the dimensions are constant, it is a vector bundle. So that's like an old fact from the work of Kodaira and Spencer on deformation theory, at least.
I guess you got just a coherent sheaf of
No, this won't even be a sheaf. So these things will not be the germs of sections of a
But if
sheaf.
you have finite dimensions, if you have compact fibers, it's a proper map, then
No, the direct image sheaf, only the sections that are locally extendable will give you a coherent sheaf. So you have a problem. So what happens here is that the dimension the dimension is supposed to be, it will always be upper semi-continuous for these things, but the problem is it might not be lower semi-continuous. Anyway, yeah. Okay, so I don't know if I don't want to go down that rabbit hole. It's too long of a discussion, but I want to talk about two special cases. The first one, so both of these are work of Bergman. The first one is if you have a trivial family. So that means that this X is some X0 cross B, and the map pi is just the projection to the second factor. Then you also, see, trivial family could be on various levels. So this thing also has a line bundle over the total space. The line bundle might not be trivial, but I want to even make that trivial because I don't know what to do if it's not. So I start with a line bundle L0 over X0, and then I can pull it back by the projection to the first factor, and that'll be my line bundle L over X. So that's the way of writing down the trivial family. So all the fibers are the same as L0, and now the only thing I want to vary is the metric. So H, the general metric for L to X, and now I can, this looks promising, but even here I don't have enough information to say that it's locally trivial. So I need to assume even more. So what I need to assume from this X0 is that X0 is some, say, open subset of some Stein manifold, or if you prefer, it's a strictly pseudo-convex domain. So this thing would be a pseudo-convex domain in Cn, and this would be some relatively compact subset, which is also pseudo-convex. I need it to have some kind of a collar, because I also will need the metric H to be the restriction from, so Y0 cross B. So from some larger space. So smooth up to the boundary, the vertical boundary here. And the reason you want to do that is because if you now have a smooth metric, so this space here is some subset of these holomorphic sections. And the point is that if the metric extends smoothly up to the boundary, then that subspace will not change as you vary B. Because if you have any two different metrics for the same space, I mean, their ratio is some kind of a function that's going to be bounded. So everything's going to be in the same L2 space. So this actually gives you not only a locally trivial, but a trivial vector bundle. Okay. Theorem from 2009 is that so if the metric H has non-negative curvature, then this vector bundle with its L2 metric has non-negative curvature in the strongest possible sense. Okay, so the proof of this is really beautiful, but it's appropriate for a seminar, maybe not for a colloquium, so I'll skip that. But I just want to tell you that this theorem has a tremendous number of applications. So I have to say it a little bit fast. So this strong notion of positivity is stronger than a weaker notion of positivity called Griffith's positivity. And Griffith's positivity says that, so if, say, lambda is a holomorphic section of, say, the dual vector bundle, then you can take the norm of this lambda, say, with respect to the dual metric, the dual L2 metric, and then you can take log of this thing, and the statement is that this thing is plurisubharmonic. So if you don't know what plurisubharmonic is, it doesn't matter that much. This says that there's a kind of convexity to the logarithm of the norm of a section of the dual. Now, there are very interesting sections, holomorphic sections of the dual. One of them is evaluation at a point on x0. It's a little more than that, but let me just say, if you compute the norm of the point evaluation, that'll give you the Bergman kernel. So this tells you that the log of the Bergman kernels vary plurisubharmonically with respect to this base variable. So you have a kind of convexity property for how these kernels can vary. Okay, that's maybe a little bit niche for several complex variables. Another thing that you can look at is so you can consider the problem of L2 extension of holomorphic sections. So maybe you have a holomorphic section of L over the central fiber, which is living in this space. So it's a section of Kx tensor L, and you want to extend it to a section in the family. Then you can assume that there is such an extension. You can look at the minimal norm extension, and you look at that minimal norm of the extension operator, and that's one of these sections. So it gives you a new proof, and actually a sharpened proof. So it sharpens famous L2 extension result of Osawa Takegoshi, which has had a tremendous number of applications in analytic and algebraic geometry. There's also an ideal membership problem. So if you're given a bunch of holomorphic functions, you want to determine the ideal defined by them. And there's a famous theorem by Henri Skoda about giving, if you have certain L2 estimates, then you can, if some function satisfies L2 estimates, then it's in this ideal. That theorem is extremely technical. It was a kind of L2 attempt at the corona problem in several variables. At the time, that's what was exciting about it. But it's had other applications since. But the proof was very technical. But if you use this theorem here with an appropriate, well, it's quite complicated, but so there's a new proof by Roberto Albesiano. So he's here. You can ask him about it if you want. So it's a very nice piece of work. The clever thing here is to find how these sections operate with this theorem, to find the right sections to give the proof of the theorem. But it's an extremely powerful tool. Okay, so that's the first situation. So second situation, second theorem of Bergman considers when, this is what Claude asked about, when this map is actually also proper. So the fibers are compact manifolds, and then you actually have a family of finite dimensional vector spaces, and you would like to know if that's a vector bundle. And as Claude told us, it's not going to be a vector bundle in general. These dimensions don't have to be constant. But if the curvature is, the curvature of the metric is non-negative, then this theorem here, which can be proved using the first theorem, actually implies that any section extends to a neighborhood. So now if you take a basis of sections and extend it to a neighborhood, it's going to remain independent. So you get the lower semi-continuity of the dimensions. The upper semi-continuity is basically Montel's theorem. So you get the local triviality, and you actually get a vector bundle. So I don't want to keep people too long. I'll say that, so what Bergman did was he computed the curvature explicitly, and then he used Hodge theory to prove that it was positive when the metric had non-negative curvature. But it also involves the Kodaira-Spencer class of the family, and the formula is somewhat involved. So that's how Bergman proved the second theorem. The first theorem is proved in a completely different way. So the first theorem, if you try to form this vector bundle here without the holomorphic condition over a trivial family, it's still going to give you a locally trivial vector bundle. So it will naturally have a holomorphic structure. And in that case, the curvature is very easy to calculate. So it's just a multiplier operator coming from the curvature of the metric. So you've got this easy to calculate curvature operator. And then you have an old formula of Gauss that was adapted to the complex setting by Griffiths. It's sometimes called the Gauss-Griffiths formula, that tells you that the difference of the curvature of a vector bundle and a subbundle is the square norm of some second fundamental form. So you try to estimate this second fundamental form, and it turns out that Hormander's L2 estimates make that almost trivial. So that estimate goes into estimating this curvature as a difference of a curvature, a very simple curvature minus a second fundamental form. In this situation here, if you try to go to these kinds of spaces where you remove the holomorphic condition, well, actually Ehresmann's theorem will tell you in the proper case that all the fibers are diffeomorphic to one another. And in fact, it's not hard to show that the resulting thing with L2 spaces will actually be a smooth vector bundle. But the problem is there are no complex structures that are obvious for it. Well, so this is what Bergman wrote in his article. He said, I don't know how to find a complex structure, so instead I just computed the curvature explicitly. It's kind of a mess, but it all comes together, and then I can estimate it using Hodge theory. So I kind of got interested in that because I loved the proof of that first theorem, and I wanted to try to do a similar thing for this second situation. So, and I discovered that in fact there's not just one natural, well, there's no one natural complex structure for the L2 bundle. So the L2, maybe I could write it as L2 of H. So this has uncountably many, so a huge number, huge collection of holomorphic, well, complex structures. So you want to know how to compute d bar of a section in some direction in the base. So what you want to do then is you want to lift a tangent vector on the base to the total space and differentiate with respect to that. And so for that, what you need is a distribution in the tangent bundle. And if you've got such a distribution, you can define a d-bar operator. That d-bar operator will square to 0 if and only if the distribution is integrable. These are all not obvious things that you have to calculate. But when you do that, you can actually start to try to write down formulas. And if you, maybe there's just a whole lot that goes into it. But in the case where the curvature of x is non-negative, everything works out nicely, and you actually get an analog of the Gauss-Griffiths formula in this proper setting. So it gives a much more transparent proof. Also, the formula that you get is more complicated than Berenson's. So it's when you put everything together that a bunch of things cancel out. So you actually learn something about the geometry, but you might just say, well, it's just a new proof of a known theorem, so why do you care? Well, I can't 100% answer that yet, but one thing I can tell you is even if this curvature is not positive, you can sort of push this theory through. But you have to invent a whole new kind of geometry for these families of Bergman spaces that I've been working on, mostly with Pranav. So we've been studying these structures that we call BLS. So this is for Berenson, Lempert, and Cirque. So Lempert and Cirque figured out how to kind of define the smooth structure of these infinite dimensional almost vector bundles. And Berenson was the one who introduced the complex structures. So combining those, we sort of created this geometry in which you can phrase all these things. So I did it for this proper case, and then Pranav studied the case where you have manifolds with smooth boundary. And this is 100 times more complicated because you need a kind of Hodge theorem, and they're just not true for manifolds with smooth boundary unless you know something about the boundary. So he made a standard assumption about the boundary, which is called compactness for the D-bar-Neumann problem. And that gives him a strong enough Hodge theorem to do a lot of things, but it's still a lot more involved. So we get theorems that compute the curvature, and we get some applications, but it's just the beginning. So I hope that there will be many more applications in the coming months. So, okay, thanks.